Okay, so in this session we cover the mean value theorem. I'll cover the Rolle's theorem first, which is sort of a baby version of and it's used to prove the mean value theorem. The Rolle's theorem is sort of a special case of the mean value theorem. Okay, so let me start by giving you a scenario. You get a fine for speeding in your car, okay? So if you want a nice discussion of the speeding fine issue, there's a video called Theorem of the Mean Policeman about the mean value theorem, and I've given you the link here in the notes. Okay, so the scenario goes something like this. You get on the motorway, and presumably there's some sort of a timestamp on the slip of paper that they give you. You get off of the motorway at some toll plaza, and again, they know what time you've arrived, right? So in principle, you could work out how much it took you to get from one toll plaza to the next toll plaza, and we know how much distance that is. And so an average speed can be worked out, okay? Now, let's say that the limit on the motorway for your vehicle was 120 kilometers per hour. And let's say that your average speed, you know, at the toll plaza, at the final toll plaza, the workout was 130 kilometers per hour. So your average speed exceeded the speed limit that's posted on the motorway. So the question is, should you get a fine? All right, right? So they hand you a 700 rupee fine, okay? Now you've taken a few calculus classes, so you say, oh, hold on a second. The speed that's posted at various points along the motorway, the speed limit that's posted, that's for instantaneous speed. What you've calculated here is an average speed. And these are two different things, right? You didn't get me with the radar gun. You got me with this, you said that my average speed exceeded the allowed limit. But that limit is for instantaneous speeds. So these are two different things now, you know, so you shouldn't give me a fine. Okay? So does that argument work? Well, it doesn't work because the person giving you the speeding fine has taken the entire calculus course and he knows the mean value theorem, okay? Which gives us a relationship for some functions between their instantaneous rates of change and the average rate of change. Okay, so let's talk a little bit about rates of change. By average rate of change, what I mean is that you have a function, it's defined on a closed interval from A to B. Then one way of defining the average rate of change is f of b minus f of a over the length of the interval b minus a. Okay, so that's one way to define an average rate of change of a function over an interval, closed interval from A to B. Okay. Now, the rate of change that we've been talking about, these derivatives, those are instantaneous rates of change. So we are talking about there's some c, which is in this interval from A to B, and the instantaneous rate of change at x is equal to c is this derivative, the derivative of f at x is equal to c. Okay. Are there any questions so far? Okay, so these are two different things. What the mean value theorem does is it gives you a chance, it gives you a way of a link between these two things. Okay.
So can you go back to the previous slide first?
Yeah.
It's all good, sir.
Okay. All right. So two different things. Instantaneous rate of change, it's the derivative at a point, and the average rate of change, which is an average rate of change over the entire interval. Okay, and if I'm going to give you a speeding fine, I have to find some link or some connection between I have to be able to argue that this average rate of change, this average speed of yours, and the instantaneous speeds that you had, which presumably could have changed at every instant, there's some connection between these two things. Okay, so Basit has a question?
No, no, sir.
Okay, all right.
I think I accidentally raised my hand. I'm sorry.
All right, so the Rolle's theorem, okay, it's the first theorem that we're going to do. And then we're going to use the Rolle's theorem to prove the mean value theorem. So this is actually a specialized case of the mean value theorem. Okay, so I want you to remember something. There was an extreme value theorem that we had, which said that if f is continuous on the interval from a to b, including a, including b, this is the closed interval, then f achieves a maximum at least once on the closed interval, and it achieves a minimum at least once on the closed interval. Okay, it might do that several times. And this depends upon f being continuous, okay? So this is a property of continuous functions over a closed interval. So I'm asking you to recall that because I'm going to need this in a minute. Okay, so Rolle's theorem. Rolle's theorem says that if f is continuous on the closed interval from a to b, and it's differentiable on the open interval from a to b, so from a to b, but not including a and not including b, and if f of a is equal to f of b, if the value of if the value of f at the starting point and the value at the end point of the interval are the same, so if all of these things are true in this if part, then there is some point in the open interval from a to b, c, such that the derivative of f at c is equal to 0. Okay? Note something. If f of a is equal to f of b, then what's the average rate of change of the function over the closed interval from a to b?
0.
0, right? Because you've got f of b minus f of a over b minus a, and f of b minus f of a is 0 in this case. So what this is saying is that if you've got this continuous function and it's differentiable on the closed interval, on the open interval, the interior of this interval, then the average rate of change is 0, and at some point in the open interval, the instantaneous rate of change is also 0. Okay?
Yes, sir.
Yeah.
So can you repeat this last line? Then there is a C. What is C here?
C is some point between A and B, not including A and not including B.
So, sir, for an example of this would be a graph of x square.
No, at the endpoints you have to have the same values. So if you took sine of x from 0 to pi, sine of 0 is 0, sine of pi is 0, right? And the sine function is continuous from 0 to pi, is differentiable on open 0 to pi, and its value at the endpoints are both 0. And then there is some point between 0 and pi such that the derivative of sine is equal to 0. And that's said, in this case, it's easy to work out that point is pi over 2. Okay, so The average rate of change of the sine function from 0 to pi is 0, and there's at least one point where the instantaneous rate of change of the sine function from 0 to pi is also 0.
Sir?
Yeah.
Sir, on what basis does it equal f of a equals f of b?
No, I'm just saying that if you have such a function, right? There are some functions like this, like the sine function is sine of 0 is the same as sine of pi, for example. Okay. All right. So remember, if you're going to apply a theorem, before you can use the then part, all of the if part has to be true. Okay? So let me ask,
Sir,
yeah.
sir, the graph of x square, isn't it same like it go from, if we take from -3 to +3, wouldn't it achieve the same value of y
Okay,
on that?
right. If it goes from if you take your closed interval from -3 to +3, then that would also be true. And the point at which the derivative is 0 would be 0.
Yep.
Okay? All right. So let me ask you. Supposing that I've got this function, y of x equals x to the 5th plus x cubed plus 7x minus 2 on the closed interval from -1 to 1. Okay? Does Rolle's theorem say anything about this function? Can I use Rolle's theorem? In order to use Rolle's theorem, the function has to be continuous on closed AB, all right? So is this function continuous on -1, 1?
Yes.
Yes,
Yes,
because
the polynomials are continuous.
polynomials are continuous everywhere. No problem. Is it differentiable on the open interval from -1 to 1? Yes, because polynomial functions have a derivative everywhere. So in particular, they have a derivative on this particular open interval. Is y of -1 equal to y of 1?
No.
Yeah, I think it isn't. So Rolle's theorem, you couldn't apply Rolle's theorem here. Okay. Okay, y equals absolute value of x on -1 to 1. Can I apply Rolle's theorem here?
No, sir, because it isn't differentiable on x is equal to 0.
Yeah. It says, is it continuous from -1 to 1? Yes, it is. Absolute value function is continuous from -1 to 1. But it is not differentiable everywhere from -1 to 1. In particular, it's not differentiable at x is equal to 0. So we can't use this. This theorem doesn't tell us anything about.
Sir, how is it not differentiable from that point?
The
They're all polynomials.
absolute value function is not differentiable at x is equal to 0. If you try and work it out from the limit definition, the limit does not exist.
Okay.
It's got a sharp corner, basically. Okay, y equals x to the 4th on -1 to 1, including -1, but not including +1. Can I apply Rolle's theorem on this function?
No, sir.
No, I can't, because
Not a closed interval.
Rolle's theorem only holds, Rolle's theorem requires what? It requires f to be continuous on a closed interval. You have square brackets on both ends, right? Here you've got a square bracket and a round bracket. So this is being defined on a different kind of interval. So this you cannot use Rolle's theorem here. Okay. Okay. All right. So this is how the proof goes. F is continuous on closed AB. So by the extreme value theorem, it attains a maximum and a minimum somewhere from A to B. Okay. Now, F is differentiable on open A to B. So your maximum and your minimum exist somewhere on closed A to B. If they exist within open AB, let's say the max or the min is at a point C within open AB, then we know that the derivative should be equal to 0 because the function is differentiable. Okay, and we had the previous result when we were talking about extrema. Okay, now the only other option is that the max or the min is at the endpoints. So, and if the max and the min is at the endpoints and not on the interior points, then the function is a constant. And the derivative is automatically equal to 0 everywhere. Okay? So, whatever happens, okay? So, once again, this is Rolle's theorem. If f is continuous on open AB, on closed AB, and it's differentiable on open AB, and the values at the endpoints are the same, then the average rate of change will be 0, and there is some point such that and there may be many points, maybe there are infinitely many points, such that the derivative is also equal to 0. The instantaneous rate of change, there's some point at which the instantaneous rate of change is the same as the average rate of change, which is 0, the way we've described it here. Okay. All right. So f sends minus pi to pi. It's defined by f of x is equal to sine of x. So is the sine function continuous from closed minus pi to pi?
Yes.
Yes, it's continuous everywhere. Yeah. Okay. Is it differentiable from minus pi to pi, not including minus pi, not including pi?
Yes.
Yes, because it's differentiable everywhere on the real line, so it's differentiable in that interval. Yes. Okay. Is the value of this function the same at minus pi and the same at pi?
No, sir.
Is sine of minus pi the same as sine of pi?
No, sir. No.
No.
What's sine of minus
Yes, sir.
Sine of minus pi
Yes,
is
sir.
0, and sine of pi is 0. So the value of the function is the same at the endpoints. Okay? So then Rolle's theorem says, it says what? It says that somewhere in the open interval from minus pi to pi, not including minus pi, not including pi, somewhere in that interval, there's a point where the derivative of f, there's a point c, x is equal to c, where f, the derivative of f at c is equal to 0. Okay? All right, so that's basically what I've said before. The sine is continuous everywhere, so it's continuous on this subset of the reals. It's differentiable everywhere, so it's differentiable on that subset of the reals. The endpoints, the values at the endpoints are the same, and so we're allowed to apply Rolle's theorem. There's some point where the derivative, on this interval, there's some point where the derivative is equal to 0, and the derivative is easy to work out. In this case, it's the cosine. So there's some point c in the open interval from minus pi to pi where the cosine is equal to 0. Okay. Now, the mean value theorem.
Sir?
Yeah.
Sir, the part that says that there's a point C at which f dash of C equals 0, Rolle's theorem states, right?
Yeah.
And the f dash C part, that's actually the maximum or the minimum point, right? It means that there's maximum or a minimum that exists between A and B.
Yeah, our argument is that there are these maxima and minima, and where the maximum or the minimum occurs, the derivative will be equal to 0 because the function is differentiable everywhere. Yeah, so that's where the maximum or the minimum
So
is.
if the conditions don't fulfill, then that means that there is no maximum point or minimum point in between the two limits, right?
Okay, well, the thing is that the point C, this function, this theorem is not telling you where the C is or how many C's there are. So it's difficult to make an argument as to that, you know.
Yes, sir, but we know in this case that there would be two C's at pi by 2 and minus pi by 2, right?
Okay, yeah, in this, if it's a simple enough case.
Yeah.
Okay,
Sir?
Yeah.
So wouldn't the C be at 0 because minus pi and pi are open intervals, and we have to find a point which is in that open interval that has a
yeah,
derivative
I mean,
equal to
no,
0.
the thing is that in general, you will not be able to work out where C is. You just know that something exists in the open interval, but you don't know exactly where, unless you have a very simple function to work with. Okay. Mean value theorem. If f is continuous on the closed interval from a to b and differentiable on open AB, now I'm not requiring f to have the same values at the endpoints. Then there is a C in the open interval AB such that the instantaneous rate of change of f at C is equal to the average rate of change of f over the interval. This is where the speeding fine comes in. They say, no, look, this is the average rate, which is above the allowed instantaneous rate of change. But at some point, according to the mean value theorem, at some point, your instantaneous rate of change must have been equal to this average rate of change. And so your instantaneous rate of change, at least at some point, we don't know which point, but at some point, your instantaneous rate of change also exceeded the allowed limit. All right.
Sir, so the difference between this and the previous theorem is that FA is not equals to FB. We don't
F of B
require
does
that
not
term.
have to be equal to F of B,
Oh, yeah.
right?
Okay.
So it's saying that the instantaneous rate of change at this C, you don't know where C is equal to, and at least one point, is equal to the average rate of change of the function.
So,
Yeah. Is there a question?
so I wanted to ask for an example of this function, of
Okay.
this theorem.
All right, here we go. Here's this function. It's defined from -1 to 2. Okay. The graph of the function is the blue there. Okay. The green line is the tangent line at some point. And the red line is the secant line. It's connecting the values at the endpoints, right? So the slope of that red line is the average rate of change. And there's a point in here where the average rate of change is in fact equal to the instantaneous rate of change. And that's where the tangent line has been drawn. You see that those two lines are parallel to each other. Yeah. Okay. So this function is continuous from -1 to 2. Polynomials are continuous everywhere. So it's continuous from -1 to 2. It's differentiable on open -1 to 2 because polynomials are differentiable everywhere. Okay. And so there is some point C, wherever that point is, on the open interval from -1 to 2, such that the derivative of f prime of C is in fact equal to the average rate of change of this function. Okay. Any questions about this? Okay. All right. So like I said, it's polynomial function, continuous everywhere, differentiable everywhere. So continuous on closed -1 to 2 and differentiable on open -1 to 2. Okay. So this says that there is a C somewhere. Okay, I've made a misprint here. This should be with round brackets. There's a C in round bracket -1 to 2 round bracket such that y prime of C is equal to the average rate of change is y of 2 minus y of -1 over 2 minus -1. Okay, y of 2 is 14. Y of -1 is 2. And what's the derivative? Well, in general, the derivative is 3x squared plus 4x minus 1. So at the point C, That gives you 3c squared plus 4c minus 1. That's equal to the average rate of change, 14 minus 2 over the interval is of length 3, and that's equal to 4. Okay? So somewhere on the interval, this, once again, this is a misprint. This should be with round brackets, open minus 1 to 2. We have that for some c in open minus 1 to 2, 3c squared plus 4c minus 1 is equal to 4. Okay, that's what the mean value theorem tells you. Any questions about that? Okay. Does Bastard have a question?
Sir, we can find our value of C through this, right? By solving this quadratic equation.
Yeah, right. You could find it through this quadratic equation. Okay. The proof runs something like this. I'm going to invent a new function from this function f, and this new function will obey the rules to apply the Rolle's theorem. Okay. So I define a new function, f of x minus f of a minus the average rate of change times x minus a. G is continuous on open AB and it's differentiable on, G is continuous on closed AB and it's differentiable on open AB. Why? Because it's made up of pieces of f, right? This is f, this is a constant, minus a constant times x minus a. And the assumption about f is that it was continuous.
Sir,
yeah.
So what can you start from the part where you said you would invent some function?
Yeah, this g of x is the new function that I'm inventing.
To prove the mean value theorem.
To prove the mean value theorem. And it's going to satisfy the requirements for applying Rolle's theorem. So I'm going to use Rolle's theorem to prove the mean value theorem. Okay, so now if I put in g of a, the way I've defined it, if I put in x is equal to a, then g of a is this, which works out to 0. And the way I've defined g, it turns out that g of b is equal to 0. Okay? So now I can apply Rolle's theorem because you have the same values at the endpoints. It's continuous on the closed interval. It's differentiable on the open interval. That means that there's some points such that g prime of c equals f prime of c minus the average rate of change equals 0. Okay, then I move the average rate of change over to the other side. So that means there's some point in c such that the instantaneous rate of change at c is equal to the average rate of change of c of the function. Okay, I just want you to feel that we're not just making things up, right? There is actually proof for these results. Okay, so back to the speeding fine. If we make the assumption that your position, right, speed is the change in distance with respect to time, right? So if we make the assumption that the distance is a continuous function of time, and in fact it's a differentiable function of time, then we can apply the mean value theorem, and then we can come to the conclusion that we actually ought to give you a fine. Okay. Okay, so one of the applications of the mean value theorem is that it tells us something about functions with derivative 0. So far, the functions that we've seen with derivative 0 are what kind of functions? What sorts of functions, when we take their derivative, give us 0?
Constant functions?
Constant functions, right? So right, so the only functions we've seen so far, which would give us 0 over an interval, 0 everywhere over an interval, are functions which are constant over that interval. Could there be any other functions that do this? Okay. So constant functions over an interval have 0 derivative over the interval. Are there any other functions which are not constant, which have derivative 0 over an entire interval? Okay. So we can actually show that our intuition is correct. That when derivative is 0 over an interval, then that function is constant over an interval. Okay. So we're going to prove a simple result. Suppose that f is continuous on closed AB and it's differentiable on open AB. And suppose that its derivative is equal to 0 for all x in AB. And then f of A is equal to f of B. Okay. All right. So the way we've stated it, the mean value of theorem applies. So there is a C in AB such that the derivative at C, which is 0, is equal to f of B minus f of A over B minus A. But if f of B minus f of A over B minus A is equal to 0, then that implies that f of B minus f of A is equal to 0. And that implies that f of B equals f of A. Okay?
Sir, I couldn't understand the previous thing you told from prior to this.
If I have, let's say I have a function and it satisfies the requirements for Rolle's theorem, and everywhere on the interval its derivative is equal to 0. Then I would like to show that f of A is equal to f of B. Okay? So we can apply the mean value theorem. And what that says is that there is a C in B so that the derivative at C is equal to the average rate of change. Now we said that this is a theorem such that its derivative is 0 everywhere on the interior points. So that means 0 is equal to f of B minus f of A over B minus A. Now for a function like this to be 0, you must have the numerator equal to 0. So that means f of B minus f of A is equal to 0. But if f of B minus f of A is equal to 0, then f of B is equal to f of A. Okay? Now, let's try, we can get a stronger result. Yeah, Basit has a question?
Yeah, that's the straight line, right?
Yeah, it'll be, the graph will look like a straight line, yes. But right now, all we've done is prove that the function takes the same value at the endpoints, right? Now we'll show that the graph should be a straight line. Once again, if f is continuous on the closed interval and it's differentiable on the open interval, and the derivative is equal to 0 for all interior points, that should be round brackets, not square brackets, then f is constant from A to B, okay? And the way you do it is you consider a smaller interval, say from A to Y. This is a subinterval. Then since f was continuous and differentiable from A to B, and Y is some number between A and B, then it's continuous and differentiable from A to Y. And we already said that the derivative was 0 everywhere between A and B. So the derivative is 0 everywhere between A and Y. Then by the previous result, f of Y is equal to f of A. and y could be any value in between a and b, right? So at every point from a to b, the value of such a function is equal to f of a. So it's constant. So if you have a function which has a zero derivative everywhere from a to b, then that function must be constant from a to b. So our sort of intuition that it should be a constant is in fact correct, and it can be proven from the mean value theorem. Okay. All right. So let's try and get a result like this. Okay. I claim that you can use the mean value theorem to do this. And how about I give you 2 minutes to think about how you might use the mean value theorem to do this problem. Okay. Okay. Does somebody have an idea of where to start?
So define f of x as cos x.
Okay. So we define f of x is equal to cos x on what interval?
A to b.
On the closed interval from a to b, right? Is it continuous on the closed interval from a to b?
Yes, cos is continuous everywhere.
Continuous everywhere, right. Is it differentiable on the open interval from a to b?
Yes.
Cos is differentiable everywhere.
Sure, cos is differentiable everywhere, so it's differentiable on any open interval that you might think of. Okay. Can I apply the mean value theorem then?
Yes, we can apply.
Yes, we can. Okay. All right, so it's continuous on a from closed AB and it's differentiable on open AB. I'm allowed to apply the mean value theorem. So what does the mean value theorem say? There is a point C somewhere between A and B such that what? F prime of C
the derivative of cos of x is equal to 0
No, mean
at
value
some point.
doesn't.
Equals to f of b minus f of a over b
Yeah,
minus.
right. There is a c such that the derivative at c is equal to f of b minus f of a over b minus a. Okay? So f of b is cos b minus f of a is cos a divided by b minus a is equal to the derivative of cosine is minus sine. So the instantaneous rate of change at c is minus sine of c. Is that okay?
Yes, sir.
Okay. Now that's kind of looking like what we were talking about, right? Yeah. Okay. So now let me multiply this through by b minus a on both sides, okay? So I'll get cos of b minus cos of a is equal to minus c times b minus a. Now I can take the absolute value on both sides, right? So I'll get absolute value of cos of b minus cos of a is equal to minus the absolute value of minus c times the absolute value of b minus a. Now, how big can the sine function be? The absolute value of the sine function takes what values?
1 and minus 1.
Right. Okay. So the sine function goes from -1 to +1. So the absolute value of the sine function goes from 0 to 1, right? Okay.
Yeah.
So whatever value the absolute value of sine of c has, that's less than or equal to 1. So that means absolute value of minus sine of c times absolute value of b minus a, that must be less than or equal to b minus a. If the sine function had given you 1, then it would be equal. Otherwise, it gives you numbers which are less than 1. So it'd be less than, that would be the less than case. So now we know that absolute value of cos of b minus cos of a is less than or equal to the absolute value of b minus a. Okay? We're using the fact that the absolute value of the sine function always takes values less than or equal to 1.
Sir, I did not understand this part.
Okay. Supposing that I've got something like x times y, absolute value of x times y, right? And I know that the values of absolute value of x go between 0 and 1. Okay? So absolute value of x is less than 1, less than or equal to 1, right? So if I multiply absolute value of x times absolute value of y, then the absolute value of x times the absolute value of y must be less than or equal to 1 times the absolute value of y, which is the absolute value of y. Is that okay?
Yes, sir.
Yeah, okay. All right. Here's a question. Can I apply the mean value theorem to f of x equals 1 over x defined from -1 to 1?
No.
No, because it's not even defined at 0, right? Let alone differentiable at 0. Right. Okay. F of x equals absolute value of x minus 5 from -10 to 12. Can I apply the mean value theorem?
No, sir.
Sir, why is that a no?
At 5,
It's not continuous?
this function is not
Yeah.
differentiable.
X is not differentiable.
5.
It's not differentiable.
Okay, this problem.
So can you please repeat that?
Yeah. So the
This one.
absolute value of x minus 5, when x is equal to 5, that's, you're going to get a corner in the graph, right? It won't be differentiable there. And 5 is in the domain.
Sir, to the conditions, if the mean value theorem is applied, are basically that it should be continuous at that interval and it should be differentiable. And sir, what about the question above this? It was continuous and differentiable.
No, this is not continuous, and it's not
Differentiable
at zero.
at zero. Okay, sir. Okay, sir.
Okay, so this is let's not do this question exactly the way it is. Let's do another question, okay? I'll modify it. F sends reals to reals, and it's defined by f of x equals x cubed plus x. Show that f is an increasing function. Can you show that f is an increasing function? You don't even need the mean value theorem for this.
But
So
we
what-
need to have like
Yeah, its
so what we
derivative
find
is
the-
yeah, its derivative is 3x squared plus 1. And so for any x, that will be bigger than 0. So it will be an increasing function. Okay? I think maybe that's a bit more difficult than I should have you doing. No. Yeah, that one goes on to too long. Okay, let's try this one. F is continuous on closed AB. It's differentiable on open AB. The derivative is greater than 0 everywhere on the interior A to B. Show that F is strictly increasing on the interval from A to B. Okay? And what we want to show, basically when we're saying strictly increasing, what we want to show is that if you have a point C and a point D, where D is bigger than C, then F of D should be bigger than F of C. That's basically what we want to be able to do. Okay? Now, if we were given that F is continuous on AB and differentiable on the interior of AB, then F will be continuous on smaller subintervals, and it'll be differentiable on smaller subintervals. Okay? So we take some interior points C and D between A and B, with D being bigger than C. Now we apply the mean value theorem. So there's a point K between C and D such that F prime of K is equal to F of D minus F of C over D minus C. Perhaps I shouldn't have used C here because I'm using it in a different sense elsewhere. Okay. So then the derivative of K is equal to F of D minus F of C over D minus C. And then when you move things over, you would get D minus C is bigger than 0, and you were told that the derivative was bigger than 0. So multiply two positives, you'll get a positive. So that means that F of D is bigger than F of C. So if the derivative is greater than 0 everywhere on the interval, then that means that the function is strictly increasing everywhere on the interval. Okay, so this is the sort of thing that the mean value theorem is useful for. It's useful for giving you results like this. Okay, we skipped that. Similarly, if you have a function which is continuous from closed AB and it's differentiable on open AB, and the derivative is negative, then that means that the function is strictly decreasing everywhere. So if you take a point and then you take another point further to the right on the x-axis, then you will get a smaller value. Okay, similar to the one that we covered. Okay, so that's what I would like to cover today. If you have questions, stick around. Otherwise, good luck on
Sir,
your
the
test. Yes.
Sir, the slides that you left behind, they were we'll study them later.
Well, you can. I mean, you probably won't get anything that
Difficult. Okay, sir. Okay, sir.
Was this a revision class or have you taught us something new?
No, this lecture is all new. Yeah.
So this
So
isn't
this is
included?
not in. Yeah, it's not included as far as the syllabus says.
No, it's not on the test. No.
Sir?
Yeah.
Where can you move to the slide 38? I need to confirm one thing.
Okay.
One before it, sir. So, sir, we would write that f continuous is on A and B and differentiable on open interval. So x, so what is the notation x? The last one for all x, including A and Y.
No, this should be the open interval. And that's a misprint.
That's a misprint, right?
Yeah. I'll try and correct the notes.
Plus, sir, can you tell us any specific topic that we were going to be tested on more than the other topics, like on which particular topic could we pay more attention?
No, you've been given the syllabus, right? Okay, if there are no more questions, yeah.
Sir, for the midterm, there was written that the allotted time for the solving MCQs is around about 20 minutes.
Yeah.
So the MCQs will be less, or we will have to do, like in 20 minutes, how many MCQs are we expecting?
A reasonable number. You won't be expected to do anything impossible.
Okay.
All right then. Good luck on your test to all of you.